Okay, so this will be my video going over myocardial contractile cells with their contraction and relaxation phases. If you're wondering why I have all these pictures from white chicks, I just thought that a funny analogy would make it easier to learn. But this will be a very simple overview, so hopefully it's not too much. Okay, so let's start with contraction. We can see here that in our contraction, very similar to skeletal muscle, we have an action potential that travels down the transverse tubules in the sarcolemmas. And then we can see here that action potentials are shaped a little differently. I'll probably do another video specifically going over the anatomy of the action potentials in myocardial cells. But anyways, okay, cool. So we see action potential going down transverse tubules until it hits these channels here. It's important to note that these are voltage-gated calcium channels. And this is a big difference from, myocardial and skeletal muscle. Whereas skeletal muscle has the DHP that opens up the ryanodine door, this one does not. This one is actually a channel itself. It lets calcium from the ECF and it allows it to travel into the ICF. Okay, so when action potential reaches these voltage-gated calcium channels in the transverse tubules, calcium will come flooding in. Calcium is like a specific key for this ryanodine receptor channel. It will unlock this door and allow it to open its gate. Ryanodine receptor channel is located on the sarcoplasmic reticulum, and we know that it is a storage depot for calcium. This is really important that myocardial cells, the whole way that they work is that they have two sources of calcium. They have the first one from the ECF. They have the second one from the sarcoplasmic reticulum. So it's two sources of calcium. One calcium, the ECF calcium, will trigger the sarcoplasmic reticulum calcium to go into the ICF as well. Okay, cool. So we have our sequence of events. Action potential comes down to voltage-gated calcium channel. Calcium from the ECF comes flooding in to the ICF until it hits our ryanodine receptor channel. It's a key to this lock. It opens its door and calcium from the sarcoplasmic reticulum will come flooding out. Two sources flooding out, and very much like skeletal muscle, it will bind to troponin, which will tell tropomyosin to move off of the actin binding sites. And if everything else is going to plan, cocking phase, power stroke, rigor state, relaxation, blah, blah, blah. All of that good stuff. Okay, so how does this tie into White Chicks? If you haven't seen the movie, I guess you could just ignore this part, but if you have, this is how I tie it in. Okay, so super, super important. We have two sources of calcium, right? Well, two sources of calcium is kind of like Tiffany and Brittany. I don't know which one is which. I'm just going to assign the names because I can't remember, but one is Tiffany, one is Brittany. So let's say Tiffany really wants to go to this club because she's trying to have a dance battle, but only she has a ticket. Ticket is action potential. Action potential is your ticket to the door to the club, your invite, and she gives it to the dude guarding the door, and he's like, okay, opens up voltage, gated calcium, she could come in. Her coming in, she knows that she cannot do this epic dance battle without her twin. Her sister, who's secretly her brother. She knows she can't do it without him. So she opens up the back door, ryanodine, to the sarcoplasmic reticulum, and now Brittany could come in too. And now they're together. Now they could do their epic dance battle. That is one of the most iconic scenes from this movie. And since they're able to do their epic dance battle, aka stimulating troponin to move tropomyosin off of these actin binding sites, that makes Latrell very happy. And one of the second most iconic scenes in this movie is Latrell, getting down with his glow sticks and whistles. And that's like him as the myosin head. He's able to cock up, power stroke, rigor state, relaxation, and then so forth. And then again and again and again. So the party is going, the club is popping. And that's contraction. Okay, cool. So how do we go from contraction to relaxation? And it's super important. Relaxation is incredibly important in cardiac muscle because, summation cannot happen. We do not want tetanus. That is fatal for everyone, right? That is fatal. We cannot have that. We need to have complete relaxation between beats, between contractions. So how do we stop that? Well, the first one is no action potential. Okay, cool. No action potential means that voltage-gated channels not being stimulated. So calcium that's coming in from here, no longer happening. That means that ryanodine is not being stimulated. So calcium that's coming from sarcoplasmic reticulum, also not happening. Okay, cool. But we have all of this leftover calcium stimulus still floating around, still binding the troponin, which is moving tropomyosin, and it's keeping it off of the actin binding sites, which means that since ATP is always present because we're alive, it's continuing contraction. We don't want that. We do not want the heart to be in a continuous contractile state. That's fatal. We need to remove this calcium stimulus. So what do we do? The first one is going to be our calcium ATP aces. And they're going to recycle, pump back, vacuum up, however you want to see it, or however you want to envision it. It's going to suck it all back up into our sarcoplasmic reticulum. We also have this really cool secondary active transporter. And this one is called the sodium calcium exchanger. It is an anti-porter. And secondary active transport means that it cannot work unless our gradient is already being established by our handy dandy, our best friend, sodium, potassium, ATPase pump. And remember, our sodium potassium pump is creating our homeostatic gradient of high sodium outside, low sodium inside, high potassium outside, low potassium inside, which allows this to work because sodium wants to come in. Sodium senses that there is a high to low gradient. A high to low gradient that this primary active transporter creates. Cool. But think of it like, I don't know if you've ever been to a Croc store during Christmas or any store at Ontario Mills during Christmas. It is horrific. And there's someone, this poor 17-year-old manning the door, super anxious, super sweaty, hating their life. And they can let people in if people come out, right? I kind of like to think of it like that, where sodium really, really wants to come in, but sodium cannot come in unless calcium comes out. And that's how this NCX works. They're able to exchange. They're antiport. They're going opposite directions of each other. So sodium will come flooding in, because it wants to do its high to low. And we really want calcium to come out because we want calcium stimulus to stop. We want contractions to stop. So calcium needs to get out, needs to get shoved out. So cool. We have those two mechanisms to remove the calcium stimulus. Now, how does this tie into white chicks? Like I said before, if you haven't seen it, okay, just ignore this part. But if you have, well, calcium leaving is kind of like when you get to that point, you go a little too far. You're like, I gotta go home. Throwing up, your head's in a toilet. It's embarrassing. It's time to go home. Party's over. Club's over. I need to go to bed. It's kind of like that. So calcium is leaving. The lowering of the calcium concentration is kind of like when Latrell finally saw the truth. He was unmasked, right? Brittany or Tiffany, I don't remember which one it was. Now we know Latrell was mostly mad that, you know, he wasn't white more than the fact that he was a man. But anyways, Latrell is no longer happy. Latrell is no longer popping and locking with his glow sticks and his whistle, aka calcium is leaving. Troponin is recovering the actin binding sites with tropomyosin. ATP has attached to the myosin head, causing it to detach, to put it in relaxed. Latrell is no longer he's no longer clubbing. He's no longer getting down. Relaxation is in full effect. And that's pretty much it. That was my very simple, hopefully funny overview of myocardial contractile cells.